Okay, welcome to the M-Cubed weekly seminar. Today, I'm very happy to have old friend and colleague, John Finnigan. John received his PhD from Australian National University in 1978. Previously, he had joined the CSIRO Division of Environmental Mechanics, where he eventually became the division head from 1989 to 95. 2001, he founded the CSIRO Center for Complex System Science, which he led until 2013. He's currently a CSIRO fellow at the CSIRO Oceans and Atmosphere branch. John has many honors, and I'll just go through a few, otherwise we won't have enough time to, I'll eat too much into his time. He's a fellow of the Australian Academy of Science, of the AGU. He's an honorary professor at the ANU, Australian National University, University of Edinburgh, and most important, he's an affiliate scientist here at M-Cubed. So for us, important for us anyway. He chairs the National Committee of Earth System Science of the Australian Academy. His research activities have ranged from the dynamics of turbulence to the role of the biosphere, atmospheric exchange, and climate dynamics. He's made major contributions to the area of plant canopy and complex terrain flows. And fortunately, that's for us, that's the subject of his talk today. So, John?
Thanks, Rich, for the kind introduction. It's nice to be back at NCAR again. Just as a contrast, my wife told me the temperature in Canberra is about 27 degrees. At the time, it was minus 20 here, so I wonder whether I'm in the right place. So I'll start by just acknowledging, I'm going to talk about a research project which has been going for, Ned says 15 years, but I think it's more like 5 years, at least the stuff I'm going to talk about now. It's been possible because of a collaboration with Ned, with Roger Shaw, who's like me, nominally retired, but it doesn't seem to mean anything except you don't get paid regularly. And Ian Harmon, my younger colleague from CSIRO. And Ned said, I better tell people why we're interested in this at all, because the audience was pretty wide. And so I'll go back a bit. There were fundamental theories of atmospheric turbulence developed in Russia in the 40s and 50s by Kolmogorov, Monin, and Obukhov. And these, using dimensional and similarity analysis, they were linking the turbulent fluxes to the mean gradients of momentum and scalars near the surface. And there was then a quest to try to see whether these theories actually worked, and then to supply the empirical constants that would turn these similarity things into usable formula. And that was the impetus for several experiments in Australia, but the pivotal one was in Kansas in 1968, when for the first time reliable sonic anemometers were able to measure the fluxes at the same time as other instruments could measure the gradients. And 70 years on, Monin-Obukhov similarity theory is still the basis of model parameterizations, momentum, energy, and carbon exchange in climate and weather models. But there are also still gaps in our fundamental understanding of why MOST works the way it does. And just as another point, we're going to talk about the flow of tall canopies. And 30% of the Earth's surface is covered with forests. So we need to understand how Monin-Obukhov theory works over tall canopies. And complementary to that, these forests currently contain about most of the standing biomass of carbon on the planet. And the International FluxNet program, which is probably worth about $1.5 billion now of investment, is monitoring the carbon and energy exchange in biomes around the world. And this is a vital input to climate modeling and the prediction of where climate's going to go. So I won't go through this slide in any detail, except to say that despite all this work and these years of effort, there are still fundamental questions about canopy turbulence near the surface, such as why the ratio of the diffusivities of heat and momentum increase with instability. So we understand that at a certain level, but not at the fundamental level of eddy structure. The fact that as instability increases, the fluxes of heat and momentum decorrelate. Again, a slightly different problem to this one, but one which is rather perplexing. And the fact that the Monological formulae stop working as you come down through the surface layer close to a tall canopy. And we find that we have to actually effectively increase the eddy diffusivities of Monological theory in order to get sensible results there. So what's the reason for this, and how do we do it? So to answer these questions, and to show the results of this 5 years of effort, or maybe 15 years, whatever, we argue with Ned about that, I want to try and show you that the surface layer eddy structure, the surface layer turbulence exchange, can't be understood properly independently of the eddies, the large-scale structures that span the entire atmospheric boundary layer. So I'm showing you here animations from Ned's large-scale large eddy simulation. And in near neutral conditions, we can see that the structures well above the surface, up to the top of the boundary layer, are strongly sheared, but have some kind of characteristic structure. And near the surface, we have these repeating turbulent eddy structures of much smaller scale. In the canopy and in what's called the roughness sublayer, this region where Monological theory starts to fail. But in free convection, we have these convective plumes which go all the way through the boundary layer, but in the space between them, where there's sort of horizontal flow near the surface, we get eddies which are similar to the ones in the near neutral case. So what we're going to do in this talk is figure out how these large-scale structures and the small-scale structures couple, and as it turns out, why that coupling is actually essential to understand the dynamics of both of them. So in the rest of this talk, I'll talk first of all about the structure of these large eddies that span the whole boundary layer, and then drop down the scale and look at the structure of the coherent eddies just within and just above the canopy when the shear is high and instability down there is low. And then from there go to the opposite case. We look at the structure of the what we call canopy plume eddies. I'll explain that term as we go on, that dominate this canopy roughness sublayer layer when shear is low and instability high. And then talk about the essential coupling between these three eddy types and how that sets up transfer from the surface all the way through the ABL. And finally, some notes on the implications for modeling and tower measurements. So here are the two end members of a set of 5 domain stability classes, which are achieved by taking Ned's large-scale large eddy simulation, which is large enough to span the entire convective boundary layer or entire atmospheric boundary layer, but also detailed enough to resolve turbulence within a 20-meter plant canopy at the bottom of the boundary layer. And the stability classes are varied by changing the geostrophic wind, but keeping the solar radiation input constant at about 1,000 watts per square meter. The canopy model, the LES, is parameterized to match a walnut orchard in California, which was the site of the CHATS experiment, which is quite well known. So you can see it's quite a large-scale LES here. The output of the LES matches measurements at CHATS very well, but also it's been reparameterized to the Amazon, and it also matches results from the Atoll Tall Tower in Amazonia extremely well too. So we have a good deal of confidence what we deduce from these large eddy simulation data will be relevant to the real world. So what we see through years of experiments on the the full boundary layer on using balloons, aircraft, sounders, tank experiments, and so on. In fact, all of this work was summarized quite nicely in a paper by Peggy Lamone and authors, I think in 2020, co-authors. And what we see is that the structure of the eddies which span the boundary layer evolve with a stability parameter, which is the boundary layer depth divided by the average Oberkopf length of the surface. And when stability is low, shear is strong, the eddy structures consist of streamwise rolls that span the boundary layer. On this picture here, we're seeing at a level of about 6 canopy heights. The white areas are upwelling regions, upward movement of air, and the dark regions are downwelling regions. So we're seeing the rolls perturbing the boundary layer all the way through. When we go to the other extreme, to nearly free convection, or free convection in this case, then the rolls have transitioned to closed Rayleigh-Bernard type cells, which again span the entire boundary layer with upward movement in the walls of the cells and subsidence in the centers of the cells. So before I carry on, I've got to say something about the conceptual framework I'll use to talk about these eddies. Turbulence, as we know, is fundamentally nonlinear, but paradoxically, linear theory has been remarkably successful in describing the structure of the largest so-called energy-containing eddies. So these are spectra in log-log coordinates of streamwise and vertical velocity again from the CHATS experiment, and we're looking at the highest levels, which are at 10 canopy heights, 200 meters. And what I'm pointing out here is that the energy-containing eddies, it's probably worth saying, if we were to plot these in linear form, almost all the energy would be around here. And this stuff, which is exaggerated because of the log plot, and which we often spend a lot of time looking at because of the minus 5/3 law and the energy cascade, is actually contains very little energy, relatively. So the eddies which contain most of the energy in the turbulence are the ones which get their energy from the mean flow. In a strongly sheared flow, the energy source is a shear in the background wind, and in a free convection flow, the energy source is the buoyancy gradient. And the key thing is that these eddies, because they're the first step in which energy is taken from the mean flow and into the turbulence, share the symmetries of the fields from which they get their energy. So if you linearize the equations of motion around that mean field, so the equations describe the interaction of the turbulence with the mean field, but only treat the interaction of turbulence with itself, the turbulent interactions, in a statistical way, usually with an eddy diffusivity, then what those equations can do is tell you which of the structures, the eigenmodes so-called, that will grow preferentially given this energy availability. There are two ways you do this. One is called rapid distortion theory. The one which is more relevant here is so-called hydrodynamic stability theory. You look for, you take the background field, you introduce some small perturbations, and you look for the perturbations that grow exponentially. And then observationally, we see that those perturbations correspond to the largest eddies that span the flow. So I'll often talk about eigenmodes through this talk because these eigenmodes act as attractors for the turbulence. These patterns which are the preferential, the preferences of the mean flow to fall into act as attractors for the turbulence. There are some deeper thermodynamic reasons why this should be so, but we might just mention that at the end. For the moment, this will do. So these large-scale eddies do their thing, but they also, the footprints of the eddies, if you like, modulate conditions near the top of the canopy in the roughness sublayer and the canopy itself. So if we look at this weakly unstable flow, strong shear, we have these streamwise rolls, And we see that where the rolls are coming down to the surface, they bring high velocity air and create strong shear. And in those regions of strong shear, we have strong values of the Reynolds stress. And that's here in blue. If we go instead to the strongly unstable case, where we have ascending cell walls and descending subsiding sensors, we see that the regions of strong shear and the regions of high Reynolds stress have moved to the downwind edges of the cells, where the cell circulation reinforces the mean wind in the boundary layer. So that's where you get the strong shear. If we add on top of that the heat flux, we find that again in the weakly unstable case, where things are driven by, where it's the streamwise rolls which modulate the shear at the canopy top, the heat flux is pretty well correlated with the momentum flux, with the Reynolds stress. But if we look at the strongly unstable case, we find that the heat flux typically is more likely to be in regions of ascending plumes rather than in the regions of strong shear. So there's a spatial decorrelation of the loci of heat flux and momentum flux as instability increases. So let's park that for the moment. That's the structure of the large eddies, and the key thing to take away from that is that they evolve as stability at the domain level increases, and they modulate conditions at the top of the canopy. So let's look now at the canopy roughness sublayer eddies, and what we see there are coherent eddies that dominate turbulent transport and energy through that region. So in honor of Roger Shaw, who's sitting here, I'm going to start with a notable historical figure, which comes from an experiment at Camp Borden in Canada. When was the experiment, Roger? About 87? 86, all right. And this was one of these key diagrams which set people looking for coherent structures that span the canopy layer, which are much more evident than you see in the surface layer above, the log layer above. And you can see these these are temperature traces with time, and you can see these ramps of increasing temperature, then a sudden drop, an increasing temperature and a sudden drop. And these sudden drops can be lined up through the canopy and into the roughness sublayer above. So if you composite these by stacking together many of these traces and lining up those sudden drops, you can see that what we have is actually a scalar microfront, a sudden temperature change from warm to cold. But if you then look at the velocity vectors that go with that, you see that here, where the temperature is increasing slowly in the ramp, you are actually seeing upward movement of warmer air from the canopy towards the outer part of the floor, and then a sudden replacement of that movement by a downward gust of cooler air from above. And this upward movement with the mean velocity less than 0 and the vertical velocity greater than 0 is usually labeled an ejection, sometimes a Q2 event, whereas this downward movement of fast air, U greater than naught, U prime greater than naught, W prime less than naught, is labeled as a sweep. So sweeps and ejections were found throughout canopy and roughness sublayer turbulence in many, many experiments. But I'll jump forward now 30 years, so sweep on the 30 years of canopy turbulence history to the resolution of these questions of why are these large coherent eddies so prominent in this layer, and what's the dynamical origin of them? And there were two steps in this. One was the proposition that there was a so-called mixing layer hypothesis, where a group of us realized that the turbulent statistics at the top of a plant canopy look much more like the stats of a planar mixing layer in turbulence than a boundary layer. And following that observation, we realized that the at the top of the canopy, there's always an inflection. Get this to work. Where's it gone? Come back. Oh, there we are. There's always an inflection point in the velocity profile. Now, many of you will know this, but if you have a boundary layer profile where the velocity increases steadily, but the velocity gradient decreases with height, and you don't have any viscosity, you won't get any turbulence. That is hydrodynamically stable. If you throw in a bit of turbulence, a bit of stickiness in the fluid, so that the inertial forces can get a little bit out of phase with the pressure forces, then turbulence can develop. But if you have an inflection point in this sense, where the, come back, Pointer, yep, where the velocity increases slowly, then rapidly, then slowly again, then that is hydrodynamically unstable. So even without viscosity, that will go and produce turbulence. So we thought, well, we've got a mechanism here which adds to the normal boundary layer mechanism in producing turbulence, so maybe this is what we've got. So a lot more work went into this over the years, but we were able to identify 4 steps for a sort of a cascade of instability, of linear and nonlinear instabilities. In reality, these happen all at once, but it's nice to pick them apart. The first instability is as a Kelvin-Helmholtz instability. We have a sort of vorticity wave, which is the instability mode of this inflection velocity point. But these regions, these span-wise regions of high and low vorticity, soon clump together into so-called Stewart vortices. And these Stewart vortices affect each other in such a way that any small perturbation causes them to wrap around each other in this kind of hairpin pattern. And then, because they're in shear, these hairpin vortices get stretched, the vorticity gets amplified, and then vortex self-induction through the Biot-Savart law glues these things together. And one of the key plots that was sort of on these eureka moments in this was when we realized that this vorticity thickness, which is the velocity divided by the velocity gradient at the top of the canopy, is the key length scale of this instability. And we approximated this just by a little bit of canopy geometry. We found that there was a pretty much linear relationship between the vorticity thickness and the spacing and size of these large eddies over a range of canopies from 30-meter forests to 5-centimeter wind tunnel models. And so we thought, we may be onto something here. So we pursued this a lot farther. These are snapshots of a large eddy simulation that we analyzed, again, from Ned Patton. And what we're seeing here, we're plotting the blue lines are plots of lambda 2, which is a function of the symmetric and antisymmetric parts of the strain tensor, which sort of picks out regions of high vorticity but high solid body rotation. So we're seeing these head-down vortices, which between their legs generate a sweep and take a lot of the momentum flux, that's a red blob. On the other side, there's a head-up vortex. Between the legs of that, the circularity is such as to generate an ejection. And in between the two, the flow squashes the fields together and gives us a scalar microfront. It also produces a pulse of static pressure between those two vortices, two hairpin vortices. Go back. Okay. So that was nice and clear. I think we can probably still dig out the movies if anyone's interested. But if you move up out of the canopy roughness sublayer into the log layer, the classic surface layer above, that coherence simply disappears. So that basically that set of eigenmodes, that set of instabilities which produce that final set of stuck together head up and head down hairpins is lost as you move away from that, out of that region where the inflection point is dominating the flow. And that region where you have the domination of that inflection point instability, but loses as you move up, is called the roughness sublayer. And just taking an XZ slice through that, we get this characteristic pattern. Here's some, the red and the blue are temperature contours. You can see the vectors as well, and the scalar microfront. So an ejection, a sweep, a scalar microfront in between. Now this particular characteristic pattern actually isn't in a low stability domain. This is actually produced by sampling patches of a relatively unstable domain, strongly unstable. Zi upon L is minus 68. So we've simply gone across that field where the surface is being modulated by the large scale ABL scale structures, and picked out those regions where you get strong shear. And in those regions, even though the overall domain is unstable, we get this characteristic signature of the mixing layer eddies. And the interesting, the key thing, if you like, for modeling is that this has to be accounted for when we use Monological theory over tall canopies. So just looking at this example, the wind speed above the canopy has this classic log layer, modified by the Monological theory, where Z minus, the D is simply a displacement up into the top of the canopy because of the momentum absorption of the foliage. So Z minus D upon L, L is the Oberkopf length, and we now have to add an extra psi function to this to account for the fact that there's extra mixing caused by these coherent eddies. And we're able to do that by using that vorticity thickness, the length scale of the key instability, as an extra scaling length. So we get an extra dimensionless group, Z minus D over delta omega. And with that, we can produce a modified form of Monological theory. And in a couple of papers with my colleague Ian Harmon, we did this in 2007, 2008. And here's just three figures which show that that is what unmodified Monological theory would show. And this is in, let's see, this is Moga Forest. It's a eucalypt forest in New South Wales, and we can see that the modified theory works quite well right through the canopy. Tumbarumba is that large-scale forest that was in that very first shot, a 45-metre alpine ash forest, again in New South Wales. And this is Duke Forest, some data from Gabic et al. And that theory now has been implemented, that modification of Monological in CLM, with a paper with Gordon Bonin and Ned and others in 2018, were over 56 days, I think, of 56 site years, okay, years, not days. There was significant improvement to the model by including this kind of stuff. And in a paper by Vergeppelage in 2012, he looked at, how many? 25 studies of different canopies and found that this particular theory, the Harmon and Finnigan theory, outperformed anything else in adjusting displacement height and Z0. One of the consequences of this is that Z0 and D, the classic things that you look up in a table to plug into a model, are actually flow parameters. They vary with stability. They're not constants, geometric, determined by the geometry of the surface. That's all very well, but as I said, we got that characteristic pattern, the mixing layer eddy pattern, when we just focused on the bits of this relatively unstable domain where the shear was high and the stability Richardson number was low. When we looked at the rest of the domain, where shear was low and instability was high, that pattern disappeared completely. And we just get this mess. So we had to look a bit farther. And we discovered first of all, just by looking at instant snapshots of the flow and then doing some compositing, that even in weakly unstable flows or free convection flows, if we focus on these regions of low shear, high instability, we get a characteristic thermal plume structure. And it doesn't matter whether we're below a downdraft from the large scale flow or under an updraft, whether it's just the unstable parts of a weakly unstable domain or in free convection, we get roughly the same kind of structures. And this was interesting because the large eddy simulation, if you like, models the canopy as a uniform drag coefficient and leaf area distribution. It has no horizontal length scales in it. So why is the structure conservative in this sense? And so that's, if you like, what triggered this next phase of this study. So it sort of suggested that what we might be looking at is a Rayleigh-Bernard type instability, but with significant differences from classic Rayleigh-Bernard. So this is classic Rayleigh-Bernard. You have a hot plate below a cold plate, generates a linear, unstable temperature gradient, and that will generate turbulence if a parameter called the Rayleigh number exceeds some critical value. And this Rayleigh number includes a mixture of terms, which this dimensionless group, which is a sort of a balance between the buoyant acceleration caused because a parcel of air is a bit hotter than its surroundings, so you get a perturbation, gets a bit hotter, it wants to move. But at the same time, thermal diffusivity is trying to smear out the temperature difference and sort of kill that buoyancy, and viscosity is trying to slow it down if it does start to move. And if this happens in the canopy, you've also got to take account of canopy drag, which is also trying to slow things down once it gets moving. So that's a classic case. In the canopy case, we've got a rather more difficult thing. This is a problem called penetrative convection. So now instead of a fixed linear, temperature gradient, we have a canopy temperature gradient, which is sort of exponential within the canopy, has free convection above the canopy, and it's matched by a thermal roughness sublayer function, which I'll describe in a moment. And so we want to know whether unstable plumes, which match in some way what we've been observing, will develop in that situation. So it's always nice to try and get an analytic solution of these things. I mean, you can hit them with numerics, and I'll show you what happens when you do that in a minute. But we spent a bit of time fiddling with trying to get an analytic solution to try to pull out of this what are the key controlling features. And the way we did this is to take that realistic temperature profile there, the blue one, and match it with a hyperbolic tangent profile, which matches the temperature gradient at the top of the canopy. Because the temperature gradient is what gives you the thermal forcing in these problems, and that's the gradient of temperature, which actually is a sec squared if you have a hyperbolic tangent, and peaks just at the top of the canopy. So analysing that as a Rayleigh-Bernard stability problem, we actually got some nice answers. We found that the scale, we could produce the vertical structure of the most amplified modes of that problem, and immediately saw that the width of the temperature of the velocity perturbation was slightly wider than the width of the temperature perturbation that accompanied it, which actually matched what we'd observed from two-point correlations in our data fields. And when we looked at the variation of the Rayleigh number for both the hyperbolic tangent profile, that one, and the realistic temperature profile, the blue one, we saw that the solution said that in the canopy, just above the canopy, they were both unstable in free air, but if you add the canopy drag, then we didn't exceed the critical richness number. So things should go turbulent just in this little spot above the canopy, but in the free air. Whereas within the canopy, you don't get to a high enough Rayleigh number. The canopy drag added to the viscosity and this, the slowing down of viscosity and the smearing out of thermal diffusivity kills the perturbations before they start to grow. This is what happens with simulations of that, and you can see, look at the XZ and XY slices on the right, and you can see that just as the linear theory says, that these canopy plumes initiate in the region just above the top of the canopy and then penetrate down into the canopy as time goes on. At the moment, we're redoing these for more realistic temperature profiles. But that was sort of encouraging. So just summarizing that, these coherent roughness sublayer eddies, when shear is low and instability is high, are plumes. The size of the vertical distribution of the plumes is a reasonable match for what we observe when we parameterize the likelihood simulation and the model the same way. And we can also pull out of that the scale of the horizontal perturbation, which matches this fastest growing mode, and again is a pretty good match to the observed plumes. And so we deduce from this that these canopy plumes are linear eigenmodes of a rarely known convection instability, and the length scale of the buoyant instability is L theta, which is the, if you like, the e-folding distance of the canopy heat source, or interchangeably, if you like, the e-folding distance of radiation absorption into the canopy. So we can use this knowledge of the thermal instability process to do what we did with the vorticity thickness and produce a function to modify Monological in the region above the canopy when things are thermally unstable. So sorry for the busy slide and the equations, but you recognize the classic Monological formula where, again, Z minus D is the parameter above the canopy, Kz upon U star du dz, the dimensionless velocity gradient, is a function of Z minus D upon L, the Oberkopf length. Classic Monological stability theory. But as I said, in the roughness sublayer, these phi m functions have got to be modified by a phi m hat, a roughness sublayer phi function, to reflect this extra mixing power of having coherent eddies there. So in the case of the mixing layer eddies, in the shear eddies, this phi m hat is a function of the vorticity thickness, so that's the extra dimensionless group. And it has that particular form. So we have an exponential decay of the influence of this instability as you move up into the surface layer. But in the case of canopy plume eddies, this roughness sublayer extra phi is a function of L theta. So we have a different form. And because these two constants, this is a kind of a that's a matching constant, that's an integration constant. They have actually different forms because of the different nature of the instability calculations. So just summarising, I'm not sure what time I started, Rich.
It's 2:40.
Okay, I've got about 10 minutes to go. So just summarising where we've got to, these large-scale eddies that span the atmospheric boundary layer are linear eigenmodes of the shear and buoyancy fields. They change the structure from rows to cells as this overall stability parameter increases, and they partition the canopy roughness sublayer into regions of high and low instability. So in the regions where the shear is high and instability low, the coherent mixing layer type eddies, which are generated by the inflection point at the top of the canopy, dominate things, and the controlling length scale is this vorticity thickness. The velocity at the top of the canopy divided by the velocity gradient at the top of the canopy. And that forms a dimensionless group that you can add to Z upon L, Z minus D upon L, I should have said, to successfully modify Monological when the instability is not too high. But conversely, when the shear is low, because of these large-scale eddies, and instability is high, buoyant plumes dominate this region. And these are also eigenmodes of a different type of instability. And the controlling length scale now is this canopy heat source, e-folding distance. And that also forms a dimensionless group that you can use to modify Monological in that region. Now, the fourth thing I wanted to say was these things are essentially coupled. So if we look at those different domain level stabilities that we got by changing the geostrophic wind, and we look at the probability of there being various values of gradient Richardson number, you can see that there's not much low negative Richardson number, not much instability in the near neutral case, and not much high shear in the free convection case. I can show that better by doing that on the log-log plot, which shows the overlap between the various cases more clearly, although you have to account for the fact that the log scale means that, while you might see some overlap, there might not be many events in that case. So we have overlap between these different cases. Now, if we plot key parameters like the inverse phi function, which is related to the diffusivity for momentum, phi m, and inverse phi for heat, which is related to the diffusivity for heat, against the local Richardson number on the surface. These are in patches which are large enough for these eigenmodes to actually develop. You need a bit of space and time for them to appear out of the background. Then what we see is that in regions of overlap, in this case between strongly unstable case, which is circles, and the moderately unstable case, which are these crosses, so weakly unstable and moderately unstable, where there's some overlap, we see that we get the same values of the phi functions, even though the domain level stability is significantly different. As long as the patches are the same, then we get the same values of the critical exchange parameters of monological theory. And that goes all the way down to the near neutral case, but because the near neutral case doesn't go very unstable, you don't get many points and overlaps there. But this is an important observation, because it turns out then that it's not so much a steady deformation of the eddy structure that gives us this variation of phi h and phi m. It's rather a steady deformation, a steady change in the area fraction covered by one or the other eddy types, and that area fraction is determined by what the large-scale eddies are doing. So it has implications for parameterization. So when we see this variation of phi h and phi m, we see that this change is largely because of the change in the locus of the surface, where eddies with different effectiveness of heat and momentum transfer are located. So let me try and put all this together in, again, unfortunately, a bit of a busy slide, but I wanted to do it all on one thing. So let's look again at the large-scale structures. We have when the parameter Zi upon L is minus Zi upon L is small, near neutral. We have rolls, and the rolls bring strong shear and large momentum fluxes, and also heat fluxes down near the surface. But as that parameter increases, we transition steadily to these closed cells. And they have a different partition of the surface into high and low shear regions, high and low Richardson number regions. When the Richardson number is near neutral, then a larger part of the surface is occupied by mixing layer eddies, and typically these mixing layer eddies have a turbulent Prandtl number of around 0.8, so that the transfer efficiency, the ability to transfer heat and momentum is similar. But when we move into domains where more and more of the surface is occupied by regions of low shear and high instability, then we get canopy plumes, which typically have Prandtl numbers of around 0.4. And there's actually, something I don't have time to talk about today, a relatively abrupt transition between these two types. They're both eigenmodes of the background wind and temperature fields, and so you can't have one and the other simultaneously. There is a region of transition, but that's something to be talked about in another talk. So together, we have to look at the area of mixing layer eddies plus the area with canopy plumes, and together these determine the area average Oberkopf length. But the area average Oberkopf length feeds back into this parameter here, which determines what the ABL scale eddies are, which determine what the partition is, and so we go around, and as you can see, we've introduced another closure problem here, which wasn't there before. So, summarizing all this, what we're trying to do, because we know we have to do this, is to change the form of this roughness sublayer influence function that modify Monological theory as the eddy forms change. Going back to those pictures I showed you before, the Harman and Finnigan theory works very well as long as you don't get too unstable. But as you start to get into what we've called here sort of moderately to strongly unstable, the theory starts to break down. And it still works a bit, but for the wrong reasons, which again I don't have time to go into here. But we want to actually make a smooth transition from mixing layer near neutral modification of MOST to strongly unstable modification of Monological near the canopy. But we've got this new closure problem now, because the area of mixing layer eddies times the Oberkopf length that goes with mixing layer eddies, plus 1 minus that area times the Oberkopf length that goes with canopy plumes, determines the average, the area average Oberkopf length, but Zi upon L determines the what the area of mixing layer eddies are. So we need another piece of information to close this problem. And again, this is for another seminar, but we can do this if we assume that the atmospheric boundary as a whole self-organizes, the interaction of these three eigenmodes, self-organizes to maximize the dissipation of energy or the production of entropy. This is effectively a manifestation of the so-called principle of maximum entropy production, which has been shown to apply, at least in the case of free convection. So that's one thing, and that's where we're going with this. Another one is that the eddy flux measurements of surface exchange that we do on flux towers are subject to some unavoidable influence of, from these ABL scale turbines. You can't actually understand what's going on in the tower layer. When I started in this game, people actually used to refer to the lower layer as a tower layer because that was where most of the information was coming from then. It's impossible, for example, to close the tower energy budget without taking account explicitly of the role that the large eddies play, as the ABL scale eddies, as well as the roughness sublayer scale eddies. And the third thing is a significant change in interpretation. So smooth variation of properties like phi functions, turbulent Prandtl number, with stability, primarily reflect a smooth change in the area fractions of the surface which are occupied by mixing layer or canopy plume eddies, not a continuous deformation of the eddy form itself. As I said, the transition between mixing layer and canopy plumes is relatively abrupt. That, if you like, as a side effect, if you like, says that perhaps is not correct to treat the modelling, parameterization of the boundary layer as a series of horizontal slabs with different properties which sort of talk to each other. You can't do that because they're intimately coupled. You've actually got to treat it as one self-organizing, interacting system. It seems a good place to stop. Thanks.
We're open for questions, comments. Don.
Yeah, very interesting. How would you estimate this this length scale, delta sub omega, from observations?
We do it this way. So we find that in canopies, particularly in the upper part of canopies, the very simple H.E. Inouye 1968 model of exponential decay in the canopy, or if you like, with depth into the canopy, or even better, Ron Chonko's model, where the vertical coordinate is cumulative canopy leaf area, allows you to actually deduce what this thing LS is from just putting a tangent through the strong shear at the top of the canopy, or you can do a rather more complex calculation than that. But you get it just from some measurements of velocity profile in the canopy itself. And that's how we got that profile there. The key thing, I guess, about this, about the roughness sublayer model that we built, is that we move the thing which we consider a geometric property of the surface from being Z0 and D to actually being the momentum absorption of canopy elements, which are much less susceptible. The drag of a leaf or a stem or a branch in the canopy is hardly affected by stability. So if you take the geometric properties, including the drag coefficient and leaf area per unit volume of the foliage in the canopy as your base, then the change in Z0 and D follows simply because the stability influences on the flow above the canopy has to match what's happening within the canopy. So you have a much more robust ground for treating these classic the classic values Z0 and D that you put in models. So it's not hard to actually do that. Yep.
Another question, comment?
John, could you speculate what happens as H gets smaller and smaller down to the size of a small rock or a bush or something like that?
Yeah.
Do these same sort of ideas collapse down to the surface where it's not tall?
In a sense, yes, with some caveats, except that you're not interested because it's like Nicoraz's Sangre and Roughness. You didn't really care what was happening around, So at some point, one of the reasons you're interested in canopy floors is that things happen in the canopy. Also, you can walk through them, and it actually works in cities as well as canopies too. But as you squash it down, it still really works that way. One of the differences is that as you get down to lumps, rocks if you like, then the inflection point in the canopy, which is really a property of a relatively dense canopy, so you actually have to area average, spatially average the flow to get that smooth inflection point. So there comes a point when, if you had a canopy of lumps, if you like, where at any point the flow looks nothing like inflection point. It actually has got wakes around the canopies. Now, if you area average it, spatially average it, you'll get an inflection point, but that's not dynamically significant. And I've actually done an analysis of this. It's in a paper with Margie Bohm and Ian, saying the criteria when you flip from being the inflection point being dynamically significant, in which case the vorticity thickness is an important scale, to when it's just a set of lumps of rocks or buildings. And then what you have to think about is that the generation of the head up and head down horseshoe vortices is a different mechanism. It's to do with horizontal vortex lines wrapping around obstacles. Vortex lines can't break, so they wrap around and then spin up. Whereas in the inflection point instability, it's the actual nature of the turbulence itself. A small perturbation then causes that thing. So there is a dynamical change.
Comment.
I was actually going to ask a separate question, if that's all right. So John, thanks. Lovely. I'm just curious, Have you thought about ways to use the LES to get at that area fraction question and how we might go pursuing that from that which we already have?
I think that might have been a Dorothy Dixon. Do you use that expression here? In Parliament in Australia or in the UK, you get members of your own side to ask you a question, allows you to sort of spout about things they know you know. Yes, we have in fact done that, because Ned and I and some others were applying for a European Research Council synergy grant, and one of the things that did was to actually, Sean might be interested in this, that we were looking at how to deal with interpreting tower measurements when you were in all sorts of terrain, and concluded, basically motivated by some of the stuff I've shown you today, that you actually have to consider the boundary layer, basically from the bottom of the root zone to the top of the boundary layer and sideways to over a length scale which allows the large eddies in the boundary layer to do a few spins, so the boundary layer is adjusted to the surface. And we call that the terrestrial ecosystem planetary boundary layer system. And you can then treat that as a complex adaptive system where fast processes like some of the biological processes in the plants and the turbulence allows that whole system to adjust to more slowly varying forcing across the boundary, both from the troposphere and from things like water availability below. And so once you've set the thing up in that framework, then you're primed to use non-equilibrium thermodynamics to understand it. And the great advantage of that is because you now have a well-defined open thermodynamic system, you can apply simultaneously the first and second laws of thermodynamics to the system. And they put much stronger constraints on what can happen to energy and scale of fluxes than the first law alone. So we naturally think of conservation of energy, conservation of mass, but forcing the fact that entropy in the closed parts of the system can at best stay constant, but should actually decrease, puts a very strong constraint on that. And then you can look at the entire boundary layer as a heat engine, and if it's free convection, the thing is entirely driven by the solar radiation fluxes, and you can get the fluxes out of the boundary layer without assuming anything about parameterizing the surface exchange coefficients, because you've replaced that by a fundamental physical principle. Where we were going with that was taking the extra step of adding now a kinetic energy source from the geostrophic wind, so it becomes a heat engine plus a kinetic energy input. So that's something which is in progress, shall we say. But yes, we know how to go, and that's how the use of maximum entropy production to close that thing fixes. All right.
Thank you for the great talk.
Sorry. Yeah.
I was just wondering about the impact of radiation. So instead of like altering the geostrophic wind and keeping a constant input, a shortwave, how, for example, like the morning transition time period would affect the structures. So if you had more of a constant geostrophic forcing, but a change in the input radiation, would you see kind of a similar evolution of the boundary layer structures?
Well, so it's certainly we've chosen the easiest case first, so the dry and reasonably steady state. But yes, you do. And again, going back to that heat engine picture I was just talking about, what you have to do then is to take account of boundary layer growth as well as balancing of thermal inputs and outputs. You've actually got to look at the change of storage within the system as well. Yeah, so it's one of the many next steps, if you like. A good point.
Okay, John. Well, thank you very much.
Thanks.
Thank you, John.